Okay, full screen. Okay, so this is probably the more exciting part of the course because this is biologically inspired machine learning we're getting into. So this is actually kind of cool stuff where they actually model machine learning based on what you see in evolution and what you see in nature. So it's actually pretty cool. Anyway, so we're going to cover today, the first half is we're going to cover a topic called self-organizing maps, which is basically using neural networks in an unsupervised manner. So you've seen neural networks so far, especially in the lab, where you're using it by training a prediction model with supervised learning, so there's labels. So we're going to use neural networks here in an unsupervised capacity, so it's probably something cool to explore. And then the second half, we're going to cover what's known as evolutionary computing, which is modeling machine learning and intelligence systems based on what you see in nature and in evolution, especially with Darwinian theory. So we're going to cover genetic algorithms, which is basically you're modeling your optimization based on encoding your parameters in chromosomes and genes, and the objective is to find the best solution that will find the best solution in that framework. And then we're going to cover two topics next week, which is based on swarm intelligence, so particle swarm optimization and ant colony optimization, which we'll cover next week. But I don't want to wet your whistle with evolutionary computing for the second half of this lecture. Okay, so self-organized maps. What exactly are these? Well, they were created by a professor from the Academy of Finland called Professor Toivo Kohonen. So basically, when you ever see self-organizing maps, or sometimes you'll see them called Kohonen self-organizing feature maps, they're pretty much the same thing. Right, so it was created by a professor at the Academy of Finland named Toivo Kohonen. So sometimes people will call these Kohonen maps or self-organizing maps, they're pretty much the same thing because this is the guy who actually created them. So Toivo Kohonen from the Academy of Finland. It's, let's see here. It's actually a true quote where they say simplicity is the best policy. So the idea behind this is actually quite simple. So it's commonly a data visualization technique. So we covered stuff about dimensionality reduction last week, where you want to take high dimensional data and visualize it into a lower dimensional space. Self-organizing maps kind of operate in the same way, where you're taking high dimensional data and mapping them onto a lower dimensional space. You can infer relationships and have a meaningful representation of the data that you have in front of you. Okay, so it's a data visualization technique. And the purpose, as I just talked about, is to take high dimensional data and project it or visualize it on a lower dimensional surface. So high dimensional data, and map them, or map the data onto a lower dimensional surface. Okay, so this service is very special because if you have certain data points that get mapped onto this lower dimensional space, any points that are close to each other will exhibit similarities between them. It's almost like k-means, but not exactly. But it's a nice thing where you can map this onto a lower dimensional space, and points that are nearby will infer similarities between each other. Okay, so this surface captures geometric distances to indicate similarity, between examples. And I'll give a nice graphical example in a little bit, but I just want to prime you on the theory here. Okay? So as I talked about, it allows better visualization of your data. Of your data in seeing how examples are related to one another. To one another. Okay? So this surface, because it's based on neural networks, this surface will be a bunch of neurons, and these neurons are arranged spatially, either in a 1D line or a 2D grid, or they're arranged in a spatial way that'll infer some meaning with your data. Okay? So this surface consists of neurons. Because this is based off of neural networks, right? So SOMs. So self-organizing maps, I've given them an acronym, SOMs. right? So self-organizing, let me gotta put that up here. Yeah, SOMs. So SOMs, I'm gonna refer to as self-organizing maps, are based off of neural networks, which you're probably acquainted with by now, especially with the kernel lab. Okay? And then this is an unsupervised algorithm. So we don't have any labels. Our objective is to infer some meaning into this data. This is an unsupervised algorithm. Okay? The type that we're going to look at, it's what's known as a self-organizing feature map, or what's known as a Cohonen map. So it's pretty much the same thing. Okay? So the type we will examine is known as a, well, Cohonen after the guy who made it, self-organizing feature map. So that's the full term, but it's also known in practice as self-organizing maps. So when someone asks, someone talks about self-organizing maps or SOMs, they really mean a Cohonen self-organizing feature map. They just call it SOMs for short because that's who made it, right? Okay. So these are just feed-forward neural networks, so there's no backpropagation involved. You're only forwarding information to the nodes, and there is no hidden layer. There's only an input layer and an output layer, so it makes it a little more simple. All right. So these are feed-forward neural networks. Okay, and no hidden layers with no hidden layers. Makes it a little easier. Okay, so what I mean by this is there's only an input layer and an output layer. Input and output layer. Okay, that's cool. Okay, so the input layer, it has as many nodes as you have features. So if you have a three-dimensional, or if you have 3 features in your data, then you have 3 input nodes. If you have 6 features, you have 6 nodes. So the total number of features that you have will dictate how many input nodes you have into the input layer, which makes sense, all right? Input layer has n nodes. Yes. We'll call this capital N. Capital N nodes corresponding to n features. Okay, I'd like to point out there's no bias unit for this, just like we had before. So there's no bias unit, so there's no x0 equals 1 here. We don't consider the bias unit here. Okay. Also, the output layer, it will depend on, it'll depend on many factors, but you choose this on your own. So this is a design choice that you make before you start this algorithm. So the output layer is output layer like neurons. Okay, the number of, number of output layer neurons is chosen by you. All right. Also, the weights are also n-dimensional. So if you have n features, each of the weights for these neurons will also be of the same dimension. All right, so the weights are also, are not also, but they're n-dimensional. Okay, so they occupy the space of n. So the amount of features that you have, the weights will infer the same dimensionality. Okay, so how it works is there are connections from each node in the input layer to each node in the output layer, from each node in the input layer to each node in the output layer. Okay, but there's no connections between neurons in the output layer. So the only connections you have are from each node of the input layer to each node in the output layer. The output layer nodes themselves are not interconnected. So there's only connections from one layer to another, and they're not connected in between each layer. All right? So none of the output nodes are connected with each other. just putting this all in for now, and I'll show you, I'll draw a nice diagram for you later. Okay, so the output layer is what we call spatially arranged. So what we mean by spatially arranged is that you construct or you organize the output layer in a way that makes more sense to you. So if you want to take your data and project them onto a two-dimensional surface, then you arrange the neurons in a 2D grid. Or if it makes sense to plot your, take your data and plot it on a one-dimensional line, then you make it a one-dimensional line. So the way you structure the neurons will be based on how exactly you want to visualize this data. Sometimes you might even want to put it in a cube. It totally depends. So you just have to figure out the structure that would make most sense to you. So the output layer is spatially arranged. So what I mean by spatially arranged is, either a 1D line or a 2D grid, and so on and so forth. Okay, so arranged in a way that makes sense to you. Okay. Now in neural networks, you have weights that connect from the one node to another node, from one layer to another. How self-organizing maps work is that there are only connections going from one node to another, but each neuron itself contains the weight. So if you have 6 nodes, you only have 6 weights, where each weight or set of weights is connected to one neuron at a time. So there's no weights that connect from one neuron to another. The only weights that are contained in a self-organizing map are contained within the neuron itself. All right, so it's a little different from what you're seeing with neural networks, but they're based off the same idea. Okay, so each output neuron has weights that are n-dimensional. Okay, so there's no weights that connect, from one to another. There's only connections there for visualization, so we can actually update the map and do the training. That's just for visualization purposes, but it's each node by itself just contains a set of weights that are n-dimensional, and that's it. Okay, so weights are not found between an input layer and output layer neuron. Okay, so it's a little different, but we'll draw a nice little diagram just for illustration. So here's an example. Let's say we want to do this in 1D, a 1D line. Okay, so basically you have the input layer, so you've got a bunch of neurons here. Okay, so we have n of them, so this is your first feature coming in, your second feature coming in, third, and then we have n of them in total. Okay, so input layer. Okay, they have n features. Okay, and then we also have a bunch of neurons in the output layer, so 1, 2, okay, and as many as we want. Okay, and I guess we'll call this, small case n. Okay, and output layers. Output layer neurons. Okay, so we've got 1. Let me just draw this. Okay, so I've got 1, 2, and then there's just n of them. And there are connections between them, like you have, each one of these are connected to all the nodes. But there's no way, these connections are just here to show you that there's connection between them, and then that's how you update the actual nodes here. But there's no weights associated to them. There's only weights right at the actual neurons themselves. But these are just here for illustration. Okay? So that's 1D line. And then if you wanted a 2D grid, it's pretty much the same thing, but you have rows and columns of neurons instead of just one line. So you have 1, 2, 3, and maybe you got some down here like that. And then you also have an input layer features like this as well. I'm just going to copy this down here. Same thing. Okay, and then let me move this up. Okay, that's fine. Well, okay. And then here. Okay, and then you have connections between all the nodes. Something like that. And then, just for illustration. Something like that, okay? And then here, we have an m by n output layer. So we have m rows and n columns output layer neurons. Okay, so this would be m, and this would be n. Okay, so just just a quick, just a quick illustration. So, it depends on how you want to visualize your data. So if it makes sense to visualize your data on a 2D grid, then you make a 2D grid of neurons. If it's just a 1D grid, then you make a 1D grid of neurons and so on. So it just depends on how you want to visualize your data. Okay? So just before we start, I just want to give you some notation. Each neuron in this grid or this line has a spatial location. Okay, so we're going to start with the top left corner as being the origin. So we're going to denote that as 1, 1, and then you go horizontally for the columns. Horizontally for the columns and vertically for the rows. Okay, so notation. Each neuron has a spatial location. So you can imagine these neurons as being plotted on a Cartesian graph. Okay, so but the origin will be at the top left corner. So the top left corner would be denoted as 1, 1, and then you'd vary horizontally and vertically for the columns and the rows. Okay, so each neuron has a spatial location. Spatial location as if we plotted on a graph. Okay, so imagine the top left corner. This is in the case of 2D, and if you want to do it for 1D, then the most left case would be the origin. Imagine the top left corner as being the origin. Right, that's if you have it in 2D. But in 1D, you can imagine the leftmost point, the left end of the line, to be the origin. Okay, so in 1D, the origin is at the left of the line. Okay, so the notation, I'm going to call this n of j, or curly n. Okay, so represent each coordinate as, we'll call this ni for 1D or nij for 2D. Okay, so this is the actual physical coordinate of the neuron. So for 1D, right, this would just be 1, 2, all the way up to as many output neurons that we have. Okay, and for 2D, you can think of this as a let's call this m, not m and n, but x and y, and x is going from 1 to all the way up to m, and y is going from 1 to all the way up to n. Okay, so when you have this, when you got a 2D grid like this, 1, 2, 3. Okay, so this would be the top left corner, 1, 1, all right? This would be 3, 3. This is 1, 3. Sorry, 3, 1. No, 1, 3, yes. And 3, 1. Okay, so these are, let's see, x and, actually I'm getting this, yeah, x, we're going horizontally, my bad. I'm getting this confused with images. So this is, okay, so this is horizontal. And this is vertical. So you can think of a grid like this. So you have this here, okay? So x is going this way, y is going this way. And then this line is pretty simple. You're just going from here to here. 1, 2, all the way up to n. That's just notation. I just want to put that there for now. Okay. So this notation here refers to the physical location of where that neuron is in that grid. I just wanted to put that in. Okay, so self-organizing maps, the whole basis behind it, it's what's known as competitive learning. So that's the reason where the self-organizing comes from. So what you do is, if you have an input example, you submit it to the self-organizing map, and what it does is that only one neuron will activate at one time. So you're going to present this example to the self-organizing map, and you're going to find where it best matches inside the self-organizing map. And that neuron itself will be the one that is activated, and everything else will be dormant. So this is what we call competitive learning, where you submit an example, only one neuron is best matching to that example, and will map this input example to that location of the self-organizing map. And this unit, or this neuron that best matches between the input example and that neuron in the self-organizing map, is what's known as a best matching unit. Okay, so it's based on competitive learning. The reason why it's competitive is because all the neurons compete to try to match itself to the best of their ability to this input example. And you choose the neuron that best matches between the input example and the neuron in your self-organizing map. Okay, so it's based on competitive learning. Okay, so what you do is you're given an input example. Okay, every neuron in the output layer competes. That's why it's called competitive learning, because they're competing, right? So only one neuron gets activated or selected, if you will, in the end. Okay? This neuron is what's known as the best matching unit, or BMU for short, which I'll use for the rest of this talk. Okay, so this neuron is called the best matching unit. So when you read a lot of self-organizing map tutorials, they will call the best matching unit BMU for short, because it's, it takes a little bit of time to run up best matching unit. So BMU is a nice acronym to save time. All right? So basically what's going to happen is that you have an input example that gets mapped to some location in the self-organizing map. So the process behind self-organizing maps is that if you presented similar input examples that are kind of similar to the previous input, but are tweaked slightly different, they should map to roughly the same location in the self-organizing map. So if you change some of the numbers, if you change one of the features by maybe plus or minus 1, then it should map onto roughly the same location in the self-organizing map. So it maintains spatial similarity. So when input examples in the self-organizing map are close together, they resemble similarity when you actually take a look at the actual examples themselves. Okay, so that's a nice part of self-organizing maps. They map similarity between examples in some group in the self-organizing map. Right, okay, so the neurons that are within some neighborhood. So if you take image processing a lot, neighborhood of pixels is a term that's commonly used. Okay, so you can think of this as a neighborhood of pixels, I guess. So a neighborhood of, within some neighborhood of the best matching unit should also be similar to the input example. Okay, you want them to have some sort of similarity between them. If you tweak the input slightly, then they should map to roughly the same location. Okay, so the neurons that are within some neighborhood should also be similar to the input example. Okay, so let's see here. The weights are tuned so that similar examples map to the same neighborhood as the BMU, okay? So that's the whole point of this, which is nice. So you can actually see some really cool applications to this, okay? So if you do it this way, what I just talked about is if you have neurons that are close to each other in this physical space, they mean that the features or the actual examples should be similar as well. Okay, so by doing this, neurons close to each other imply that examples mapping to this area have some similarity between them. Okay, so that's the nice thing about this. Is basically the main point of self-organizing maps. So you can see that this is unsupervised. It learns structuring data so that when you take a look at the neurons in the grid, different locations will give you different groups of your data, so you can infer more information about that. All right. So SOMs provide a mapping. Okay. From the input feature space, as I like to call it. So when I talk about feature space, it's the actual original data that you're looking at. So we call that the feature space, or your data consists of a bunch of features, right? So from the input feature space to a region in the self-organizing map. Okay, so it's actually very similar to how the human brain works. So when you take a look at external stimuli, different parts of your brain will activate at one time. So if you're doing activities such as driving, or if you're watching a movie, or if you're eating, different parts of your brain get activated at one time. So you can think of self-organizing maps as if there are different inputs that come into the self-organizing map, they should map to a different area of your brain or the different area of an SOM, so that different similar actions or similar stimuli should map to roughly the same area in the human brain or the same area as the self-organizing map. So you can, it's actually modeled based on how the human brain thinks, which is actually a really cool thing. Okay, so this is very similar to how the human brain works. Okay, so when you're presented with external stimuli, what I mean by external stimuli is something that is external to you that you observe, you take in, and you acknowledge, and you process that. So when presented with external stimuli, okay, a different region of the brain gets activated. It's actually cool because if you listen to different kinds of music, music is one of the only things where different parts of your brain get activated based on the kind of music that you're listening to. So it's kind of cool. So classical music activates certain areas of your brain, and punk and hard rock activate other areas of your brain. So it's one of those cool things where different areas of your brain get activated depending on what music you listen to, which is actually pretty cool. Okay, so let's see here. When presented, a different region of the brain gets activated. Examples could, if you're watching a movie, if you're listening to music, if you're eating even, for example. Okay, so the whole basis of this is that similar external stimuli should map to roughly the same area in the human brain. Okay, so it's, stuff that is similar. Okay, so similar stimuli should map to the same area of the brain. So that's what it should do. Okay? So the output, so when you finally train the self-organizing map, the output will be a set of weights for each neuron where when you present an input example, it'll map to a different area on the self-organizing map, and similar examples should map to the same area. So it's kind of like a clustering algorithm, but it's actually more of a data visualization technique. But you can think of it as a clustering algorithm too. It's very similar to k-means. Okay, so the output of a self-organizing map is a set of weights and neurons that map different inputs to areas in the self-organizing map. Okay, so the property with this where similar inputs group to the same area in the self-organizing map, it's what's known as a topographically respecting self-organizing map. Okay, yes? Activities. So stimuli is something that will stimulate your brain, whether or not it's an action that's something that's happening in front of you, if you're listening to music, if there's a bright light that shines in your face, anything that will stimulate activity in your brain. It doesn't have to be sight. It could be taste, it could be ear, it could be smell. Anything that will stimulate the activity in your brain. It doesn't have to be something that you see. Anything that deals with the nervous system or you touching or feeling something is what's considered stimuli. Okay? Does that make sense? Okay. Okay, let's see here. Okay, so that is good. Okay, so enough of this talk. Let me just give you a graphical example. Okay. This is actually one of the classic examples that is actually presented in practice. So let's say we want to take a look at different poverty indexes around the world. So let's take a bunch of data such as nutrition or health or education from every single country around the world, and we want to use a self-organizing map to group similar countries together based on similar poverty statuses. Okay, so a self-organizing map is actually a pretty good application of this because you can take all these countries and group them into similar performance metrics or similar poverty statuses. Okay, so suppose we want to examine the poverty of poverty of all countries, and see what kinds of countries are grouped. Okay, so we're going to use what's known as quality of life features. So nutrition, education, health. There's a bunch of features that you can use to measure the poverty index of a particular country. So using, what's known as quality of life features. There's health, nutrition, education, and so on, okay? Okay, so it'd be nice to actually visualize this data in a self-organizing map. So take a bunch of countries with these kinds of features and see where they actually group. In the end, you'll have a nice grid of countries where similar countries are clustered into different areas, which will tell you, the same countries that are within a particular group will probably be performing the same way. Okay, so it would be nice to visualize this on a grid where countries close to each other have roughly the same poverty index or roughly the same poverty status or similar. Okay, so that might be something worth investigating. Okay, so this is a great use of a self-organizing map. Okay, so this is one possible situation of what it would look like. Okay, so here. Let me just pull this up. The font's a little screwed up, but okay. So this is what would happen. So if you take a look at this, so this is one possible outcome because the actual algorithm is randomized. So there's a randomized portion of this. So this is one possible outcome of a self-organizing map. Okay, so you can see here that once you run the algorithm, you'll see that there are certain countries that are clustered together and they perform, roughly in the same manner. So if you take a look, we have Canada and the US and Australia and Denmark and all. They're all roughly clustered in the same group, which kind of makes sense. So we probably would be doing, just as well or perhaps even better than our neighbors down south. And then you have other countries such as Argentina, Ecuador, and Mexico all the way in South America. So they're most likely going to be grouped in the same cluster as well. And then you have, Central and Eastern Europe, you have Belarus, Sweden, Italy, and then this is obviously an old map. This is roughly around 1992 because Yugoslavia doesn't exist anymore. So I like to put a little note. This is old data. Okay, this is actually circa 1992. So obviously this is going to change, but this example that they give is actually based off of 1992 data. And then you have a bunch of other countries in the extreme, like you have Nigeria, Ghana, Ethiopia. You have all those countries in Africa that are probably going to be clustered together as well. And then you have other countries such as, let's see here, Rwanda, and then Namibia, Zimbabwe, all the way in South Africa as well. So it actually makes cool sense to take all these countries and to cluster them in a self-organizing map in such a way where regions in this self-organizing map will give you similarities between countries. So if you have one country that is close to other countries in this grid, they're going to be most likely the same in terms of performance. Okay, so we arrange this in a 2D grid. Okay, so countries that share, and I'll talk about how this color coding scheme is done in a little bit. So let me just write this stuff down. So countries that share the same poverty index or similar poverty index are grouped together. Okay, so this actually gives more meaning. So if you were to take these colors and put them on a world map where, one color represents people that are poor and another color that represents people that are more wealthy, putting this on a world map doesn't make much sense. But if you were to put this into a self-organizing map, it makes a much more meaningful representation of the data that's in front of you. Okay, so gives a more meaningful representation of your data. And this is a completely unsupervised algorithm that uses neural networks, which is actually pretty cool. Okay, so if you take a look, you can consider this as a 2D grid. So this is a 2D grid, okay? And you can think of this as each output neuron would be one country that is part of this grid. So it totally depends on the application that you want. So sometimes the number of output neurons would actually be the number of expected examples that you have. Okay, so a 2D grid where each neuron is a country. Okay, so this color scheme, how this came about is each of these neurons have a weight associated to them. So when you train this self-organizing map, and in the end, each of these output neurons is going to have a set of weights that are n-dimensional, you can think of this as assigning each of these weights to be a unique color. So weights that are similar in the vicinity of one neuron should roughly have the same amount of weights, or the same weights in between them. So you can assign a particular set of weights to have a particular color. So when you vary this spatially, each color will be represented as roughly the same group of weights that are similar to each other. Okay, so let's see here. We can assign a color to each neuron based on the neuron's final weights. Okay, so you can see here that the color scheme here is that yellow or dark yellow represents countries that are considered to be good. There's very low poverty in terms of the world standard. So the coloring scheme is yellow and dark yellow. These are known as excellent. So there's not really much poverty compared to the world standard. And then you have other extremes such as green and light green. You can consider these as very good. Okay, and then you have red, what we considered average. This is the color scheme that I got from where I got this from. It's the actual Academy of Finland's website where I pulled this from. Pink you can consider as poor. Purple would be very poor. And blue is unfortunately really bad. Uh-oh. All right. So that's the coloring scheme. So if we were to take each of these countries with their mapped colors and populate the world map, or we color each of these countries based on these colors, what you'd get is this. So this would be what the world map would look like if you were to take the coloring scheme that was inferred from the self-organizing map and populate a world map such as that. So it actually makes more sense. So all these purple countries that have roughly a very poor poverty index, you can see that they're grouped in relatively the same area. And then you have countries like South Africa or in the extremes, Namibia and all that, they're all grouped over here as well. Okay, so we can also color each country on a world map with this color scheme from the self-organizing map. Okay, just wanted to show you that for illustration. That one's not necessary, but the self-organizing map one is pretty cool. Okay, so that's enough introduction here. Let's get on to the actual math behind it. But the math is actually almost non-existent. It's actually really simple. Okay, so to create a self-organizing map, okay, we're going to use 3 guiding principles to help us train a self-organizing map to recognize, or group things into different areas. Okay, to create a SOM, we need 3 guiding principles. Okay, so the first principle is competitive learning that I talked about before. Okay, competitive learning. Okay, so what you're doing here is when you present an input example into the self-organizing map, you're going to choose the best neuron that is the closest as possible to the input example. So all the neurons compete, and only one neuron wins, which is called a winner-takes-all strategy. Right? So none of the people who lose get anything. The winner takes all the winnings, right? Takes all the, takes everything. Okay? So we choose the best neuron. Okay? It's also known as the best matching unit, the BMU, as I talked about before. Okay? That represents, that best matches the example well. Okay? All right. Okay? So once you figure out the best matching unit, what you're going to do is you're going to update the weights where when you provide an input example, it should ideally map to that same location again. And any neurons that surround this best matching unit should also be updated where similar examples that are similar to the one that you presented should map in a similar area to the best matching unit. Okay, so that's what we want to do here. So it's not only just winner takes all, so there is some conciliatory prizes, or there's some consolation prizes where the weights that are around the best matching unit will update, so similar input examples will map to roughly the same area of the best matching unit. Okay, so we do a weight update so that the next time the same input is presented to the SOM, you want it to map in ideally the same location as the previous time. Okay, so as it's presented to the SOM, we should make sure this neuron is chosen. Okay, so that's the basis of competitive learning. The next rule is what's known as cooperation. And that's what I talked about, where you update the weights in the neighborhood of the best matching unit, cooperation. Okay, so when a neuron is activated, okay, neurons close in proximity, to this one get activated too, in some diminished capacity, not as strong as the best matching unit, of course. Okay, so not only does the BMU weights get updated, okay, the neighborhood of neurons also get updated. Okay, so when we meet, so in this neighborhood, what we usually apply is we apply some sort of decay, where we don't apply the same strength of the weight update to neurons that are within the neighborhood. You apply some sort of decay factor where you have your best matching unit, and then if neurons that are farther away from the best matching unit should not have a significant weight update compared to neurons that are close to the best matching unit. And the reason why you do this is because you'll allow other input examples that are dissimilar to the best matching unit to be able to have a chance to update their weights to match those other dissimilar input examples. Okay, so within this neighborhood, you apply decay, where not pixels, but neurons that are far away from this best matching unit, you don't apply as strong of a weight update as those neurons that are closer to the best matching unit. Okay, so a decay is applied where the farther the neuron is from the BMU, the less of an update we make. it makes sense too, right? Because when you have when you have external stimuli that is presented in front of you, and a part of your brain activates, the whole brain does not activate. Only a portion of the brain activates. So you want to make sure that decay is enforced. So to allow for other input examples to map to other areas of the self-organizing map. Okay. So the less of an update we make. So for example, let's say I've got a 2D grid. I've got a bunch of neurons here. Okay, so let's say for all for demonstration's sake, that this here, this is the best matching unit. Okay, so what's going to happen is that the distance from this best matching unit to all the neurons, we want to take that into account when applying the updates. So the distance between this node and the the cardinal directions, north, south, east, and west, this distance is just 1. Okay, but then when you take a look at the distances along the diagonal, this would be root 2. Okay, so these neurons, the ones that are along the diagonal, are actually a little farther than the ones along the cardinal directions. So you would apply less of an update to the neurons in the diagonal cardinal directions than the ones that are on the main directions. Okay, so this is the upper layer. Okay, so what I'm saying here is that the purple neurons get a larger update than the blue neurons.
Not backwards, sir?
Sorry? Purple, yes. Just making sure you're paying attention. There, haha. Okay, sorry. Gods are against me today. Purple neurons. Yes, so the blue neurons get a larger update than the purple neurons, yeah. Thank you. Okay, so you've got some, this here is neighborhood. Of
is that always
neurons.
the way it is?
Sorry?
Is that always the way it is, just the neurons that are...
Doesn't have to be three-dimensional. The neighborhood that you apply is a parameter that you design. So you could have like a box cutoff, or anything that's beyond like 5 positions you cut off, or you might apply like a Gaussian curve to it. Like the amount of strength that you apply is a design parameter that you choose. Some people like to just make all the updates the same. It's very uncommon. Other people like to use an exponential weighting. Other people like to use a Gaussian weighting. Like it depends on performance and what your application is. Okay, does that make sense? Okay. All right. So recall that Ni or okay, I'm gonna make this point and then I'll let you guys go for a break. Is the spatial coordinate of a neuron in the SOM. Okay. So what we're going to define is a decay function, which we'll call h. Okay, so the decay h, okay, between the best matching unit x, which I'll call x, and a neuron I or ij, depending on it's 1D or 2D, right? Is simply this. So what we usually do in practice is we apply a Gaussian weighting. So the decay for the best matching unit for an input neuron I is just e to the minus. Okay? So this is a Gaussian. So Gaussian weights are nice is because the decay is gradual over time. And then you can actually control how much of a decay you want by the standard deviation. But some people like to use exponential, some people like to use, actually a box. They actually don't like to do any decay at all. They just want to make it so that every single neuron in a neighborhood gets the same weight update, the same strength. Okay, but in this case, we're going to use a Gaussian because they're nice properties. Okay, so what you're doing is simply here is you're just finding the difference in, if you have a 1D line, let's say your spatial coordinate is at 2 and the, and the one you're looking at is 5, then the difference is just 3. Right? And then you apply this to your exponential and then you get a weight. Okay? In 2D, when we have 2 locations, I and j, It's simply, okay, it's two-dimensional now, okay? So this is actually equal to, you know, I guess I minus, again, I don't know, let's call this, and then plus, I guess if you want, do this. And then these are the spatial coordinates of the BMU, okay? I'm going to make this small x because I don't want to get it confused with that capital. Okay, so just that. So you're just taking the spatial location of the actual neurons in the SOM. Okay, so this is a Gaussian. So there are many decay functions that you're going to use, but Gaussian is the most common. So we will use Gaussian here, though there are many other functions. Okay, I'm just going to make one final point, then I'll let you guys go for a break. So the reason why the Gaussian is nice is because the decay, that's not the best matching unit. The weight of this should be 1. So if you actually subtract the coordinate of the best matching unit with itself, you get 0, and each of the 0 is 1. So the most strength that you apply is right at the best matching unit, and then all the weights that are far away from the best matching unit get a decrease in strength. And the farther away from the best matching unit, the less of an update you make. Okay? So I just want to make that final point. So at the best matching unit, okay, the decay or the strength is 1. Okay, so the most strength is applied at the BMU. Okay. All right, so I'll let you guys take a break. And then when we come back, I'll finish off the last point, and I'll cover the SOM algorithm, and then I'll do an example with you. Okay? And then we'll get on to other topics.